Hey there, MSM3. Today we are talking about how to multiply numbers that are in scientific notation. And if we want to multiply things that are in scientific notation, we want to sort of think back to multiplying fractions. Remember how we did not need a common denominator to multiply fractions? Well, we do not need a common power of 10 to multiply things in scientific notation. So, for example, when you multiply in scientific notation, the first thing that you do is you multiply the decimal numbers, the coefficients. So in this case, it would be like the 2.6 times the 6.3. Then you're going to add the exponents. Why? Because we're multiplying them. 10 to the 7th times 10 to the 4th. What you're really doing is you're adding the exponents 7 and 4 to get a 10 to the 11th. So if I multiply the coefficients, 2.6 times 6.3, I get 16.38. And if I add the exponents, I get times 10 to the 11th. Now, the only problem there is we have to check and see if it's actually in scientific notation. 16.38, too large. So I have to make this 1 power of 10 smaller, 1.638, and make the exponent 1 power of 10 larger, which would be times 10 to the 12th. And since it's a power of 10, we know that we are all set, and that would be your final answer. So let's look at a few different problems that we have down here in this chart. We're going to look at the same thing. First, we're always going to multiply the coefficients, right? The 4.4 times the 3.9. That gives us 17.16. We're also going to add the exponents, so 10 to the 6th, 10 to the 4th. That gives us an exponent of 10. So we'd say, okay, that's 17.16 times 10 to the 10th. But it's not in scientific notation. So we'd need to make this 1 power of 10 smaller, make the exponent 1 power of 10 larger, 1.716 times 10 to the 11th, and we'd be done. The next question on there, same idea, 2.8 times 0.9. Regardless of whether the actual numbers that you're multiplying are in scientific notation, for example, this one's too small, as long as it resembles scientific notation, a number multiplied by a power of 10, you can still use this method. So we've got to do the 2.8 times 0.9. We've also got to add the exponents, 8 plus negative 4. So 2.8 times 0.9, that gives us 2.52. If I add the exponents, it gives me an exponent of 4. 2.52, already a number between 1 and 10, so we'd have 2.52 times 10 to the 4th. The next one on there is 2.9 times 10 to the negative 1st and 4.6 times 10 to the 3rd. We would multiply our 2.9 and our 4.6. We are also going to need to add our exponents. So we've got to do 2.9 times 4.6. And what's tricky there is it comes out to 13.34. Adding our exponents, negative 1 plus 3, we get an exponent of 2. So we'd have 13.34 times 10 to the 2nd. And hopefully you're noticing that 13.34 is too large. We need to make it 1 power of 10 smaller and make our exponent 1 power of 10 larger, 1.334 times 10 to the 3rd. Not too terrible. Now, it's obviously not always going to be in table form. This is the same idea. But this time we've got a number that doesn't look like it's in scientific notation. And one of the strategies for that is to make it look like scientific notation. So we can write this as 2.2 times 10 to the 2nd and multiply that by 6.4 times 10 to the 5th. That's one option. Another option is just to multiply the 220 times 6.4 and then work with the result, which is obviously going to be very large, not between 1 and 10. But let's see, 2.2 times 6.4, if I multiply the coefficients, I get 14.08 times 10 to the, add my exponents, 5, 6, 7, that's a 5. And because 14.08 is not between 1 and 10, I have to make it 1 place smaller, making the exponent 1 place larger, 1.408 times 10 to the 8th. The other one, not a problem that the 0.003 is too small because overall it resembles scientific notation. I'd have to multiply those two numbers, and it's going to be 0.0174, which is far too small, times 10. If I add my exponents, the negative 3 and the negative 5, I get negative 8. And here's where I have to be really careful with my integer operations. This one is very small. I've got to make it 2 powers of 10 larger, meaning I have to make my exponent 2 powers of 10 smaller. So 1.74 times 10, negative 8, take away 2, or negative 8 plus negative 2 is going to be 10 to the negative 10. Again, integer operations, being able to add and subtract integers, very important. During the year 1988, the average American ate an average of 31 eggs. There were about 246 million Americans at that time. How many eggs were eaten by all Americans? So you're saying 31 eggs times 246 million. So I could write 246 million, or I could do 31 times 2.46 times 10. 1, 2, 3, 4, 5, 6, 7, 8. And here I've got something that's a little easier to work with, right? 31 times the 2.46. That's going to give me 76.26 times 10 to the 8th. Problem 76.26, not between 1 and 10. So if I make this 1 power of 10 smaller, I have to make the exponent 1 power of 10 larger times 10 to the 9th. And that's going to be eggs. Remember, this was a word problem, so our answer needs to have units or words in the answer. A scientist uses 1.2 times 10 to the negative 5th liters of an enzyme for one chemical reaction. The scientist wants to mix enough for 140 reactions. So we need to multiply 140 times 1.2 times 10 to the negative 5th. Now, I might suggest here 1.4 times 10 to the second times 1.2 times 10 to the negative 5th leaves me with kind of a smaller set of numbers to multiply, right? 1.4 times 1.2. And that's going to give me 1.68. So I'd have 1.68 times 10. Add my exponents, right? 10 to the second with 10 to the negative 5th is going to leave me 10 to the negative 3rd. And the best part about this is by making this choice, my number here is already between 1 and 10. Instead of doing this, which would have come out much larger, I actually ended up with an answer that was already sort of in simplest form. And it was how much of the enzyme does she need? This was measured in liters, 1.68 times 10 to the negative 3rd liters. See you in class.